Okay, hello. This is the practice problems part for chapter 5. I've got one, two, three, I think four. One, two, three, four, five, six questions total for this chapter. Uh, I missed two for chapter 4. That's why there's an extra video for that. I guess I could have like unuploaded and combined them, but I'm too lazy to actually edit anything. So I'm not going to do that. Anyways, let's get started with this problem here. First things to note, even before reading, we're given our coordinate plane as this to be positive, and these are ij, so we're just going to keep that in mind. Gravity is downwards. That's pretty obvious though. Angle here. Anyways, this is a lot of reading for stuff that doesn't actually matter, so we're going to skip ahead to just reading variables, which is something I'd recommend in the questions. Usually there's a lot of random stuff you don't actually need to know, so just look for your variables. Look for like the names of the variables. Like if it says the word acceleration, look for what it is, right? So we have mass of the block in pink, 0.2 kilograms. Inclined angle theta equals 40 degrees. There's theta. Length L equals 0.40 meters. So from the middle of the block to the edge here, that's 0.4 meters. Determine spring constant K, right? S is a displacement of the block. The first phase, S equals 0, the block is at rest against a plate MP equals 0.8 kilograms. It's compressed from its resting length by distance, delta of 0.1 meters. The instant it's released, it pushes the block up the incline. In the second phase, S greater than delta, the block is no longer in contact with the plate and slides up an incline. There's no forces from the spring in this phase. In the third phase, the block passes the end of the incline and travels as a projectile. So that's this phase. 3 here is projectile motion into a cup, and the cup is here. The block has a kinetic friction coefficient mu k equals 0.1 with the inclined surface. Negligible friction for the plate. Okay, so now onto the question. A, draw a free body diagram of the plate and of the block for the phase in which they're in contact. So let's do that. P is plate, B is block. And I'm going to draw them inclined to match our plane. So we have one force spring pushing this way. We have a force of contact between, because the block is pushing against the plate and the plate is pushing against the block. So there's a force between them, and I'm going to call that FC, C for contact. There's the normal going in the J direction, and then we have a gravity straight down, MPG. Now for the block, nice square like this. We have our force of contact like so. We have our normal. We have a force of friction which opposes motion. So this is lowercase f for friction, FK. And then we have a gravity straight down, MBG. And that's our free body diagram. If you wanted to, you could do this now. Gravity, as you can see, is not actually on the plane, like on the axes. It is offset by an angle. So you can split this into your components like this for both cases, and you get an angle here. And you're probably wondering what this angle is. Well, if we think about it, this plane is offset by 40 degrees, right? So that means that if we took an angle that, if we looked at it realistically, this looks like it's on the XY axis. This is offset by 40 degrees from an XY axis. That means this is offset by 40 degrees. So this is also theta, right? I shouldn't be saying 40 degrees. I should be saying theta for consistency's sake, but that's okay. So these are our free body diagrams for both things. And now we get on to part B. Derive an expression for the spring force exerted on the plate. So we know that spring force is equal to negative kx. But what is x in this case, right? X is equal to, well, we got to think about it here. We have, it's from the, between the plate and the block, right? So we have the block here, And we can say we have the plate here. I mean, plate down here, block here. We have a distance here, which is constant. This is delta. And then we have a variable length here, s. And then we have a variable length here, x. What can we notice about x here? X is delta minus s. So x is equal to delta minus s. What else can we notice about x? It's going in the opposite direction of the plane. It's in the negative I, meaning it's negative, so we can actually plug it in here as negative x, meaning that our fs in this case, and I'll add that subscript here as well, fs is equal to k of delta minus s. And that's all there is to part B, deriving the spring force on the plate. Okay, so on to C. Using your free body diagram, write the equations of motion for the plate and block in the I and J directions. And as you can see here, we have like hints of what phase we're in for each part of the question. So like here, we are at between 0 and delta, which is 0.1 meters. So we need for the plate and the block. So plate and block. I'm going to start with the plate in the I direction. So in the I direction, we have, if we look back here in the I direction, we have the plate will be going down and then launching up. That's acceleration, right? There will be an acceleration in the I direction. Let's look at J. Will the plate be going this way or down this way? No. So that means that it is static in the J direction and dynamic in the I direction. Oh, using the names of the courses. Yeah. Okay, that was, I don't know why I said that. You can ignore that. That was a bad joke. Anyways, so we need to get our forces. So we have, using the free body diagram, we have an Fs in the positive I, we have an Fc in the negative I, and then we have this component of gravity in the negative I, which if we use trig, this is a sine. This is the sine term of gravity. So we're going to have Fs, which I'm going to plug that in now as k of delta minus s. That's not a k. K of delta minus s minus Fc minus, and this is mass of the plate, mpg sine 30 is equal to, we have mp a, because we have acceleration. So there we go. And in the j direction, we have this total out to 0, and we can see that the normal force, for this to be 0, the normal force is equal to the cosine, or the jth component, whatever you want to call it, of the gravity. I mean the weight. I don't know why I keep saying the gravity. This is the weight, the jth component of the weight. Sorry. So n of p is equal to m of pg cosine theta. I don't know why I said 30 here. This is supposed to be theta. Okay. And now for the block, we do the same thing, I and j. Let's analyze the block now. It pushes down, it gets launched. So there's acceleration in this direction. Is there acceleration in this direction? No, there isn't. Not while we're between 0 and delta. There will be like here when it's curving, but that's like visually obvious. So we're going to have again that the jth component is a static term, and we can just analyze that now quickly. The normal force is equal to the cosine term of the weight. So NB is equal to MB cosine theta. And then for I, let's see what we have. We have FC is positive. So FC, what else do we have? Minus the sine term of the weight, minus, and we'll put that MB G sine theta, and minus friction. Now what is friction? And I'm going to put that here as a note of what friction is. Friction, specifically kinetic friction, is equal to mu k, so this is supposed to be a mu k n, and since it's on the block, this is going to be nb, right? So I'm going to substitute this in to here, and this is equal to mba, acceleration. And these accelerations are the same. And the reason we know that is because it says so in part D. So that's the answer for part C. Beforehand, it would be smarter for you to, if you were tested on this question, I would make these A's distinct, because you aren't told that you can assume they're equal because they are, but write them distinctly. Acceleration of the plate, acceleration of the block, because until you get to D, it doesn't actually tell you, and maybe you have like a really evil person grading your exam, whatever. So for D, we're still between 0 and 0.1 for the distance. Using your equations of motion, determine an expression for the acceleration of the block. Hint, the block and plate are accelerating together in this phase. That hint is very important. So first of all, we're going to be looking at the block and its acceleration term. Well, we have two equations, right? As you can see, we have a normal force here, and we have the normal force is equal to this term. So we're going to take this equation, and we're going to replace the normal force with this gravity, and I forgot a g here. So, oops, there's supposed to be a gravity here. We're going to replace it with the weight term to give us this, Fc. And if you were to be counting our equations, you would see that we have 1, 2, 3, 4, now 5 equations, right? Now, we want the acceleration, and we know they're accelerating together. What does that mean? It means we can add the terms together. So we're going to take this equation right here, and we're going to add these two. And when you add them, what happens? As you can see, we have positive Fc here and negative f of c here. Not f of, because that would make it a function. Fc here. Those cancel out. So we get that k of delta minus s, we get this whole thing, space here, plus, or minus this. Minus this is equal to, and as you can see, these both have an a term, so I'm going to drag the a out, or factor the a out, however you want to say it, mp plus mb, like so. So we have this equation, which is acceleration, or I mean, this is still the force equation. So we want acceleration. All we have to do is divide out our masses. So we can do that quickly. Just like I'll put square brackets, just to differentiate over this term. And I've got to, there we go, is equal to a. And now we have an acceleration term. This is how we calculate acceleration, right? Nice and easy. Nice and easy. That is how you solve D. This question was fun. I remember doing it for a seminar. And by question, I mean like the entire thing, not this part of the question. It was like weird. It was, you didn't plug any numbers in until E, right? So speaking of E, let's get to that. Derive an expression for the block speed as a function of s in meters. Show that at s equals delta, v of delta squared is equal to a k minus b, where a and b are constants of 0.01 meters squared over per kilogram and 1.29 meters per second squared, respectively. Okay, so we need to solve. What do we know about kinematics? Well, we know that when you have a variable acceleration, you have two equations to use. A is equal to dv dt, or we have v dv is equal to ads. Well, what do we have sitting right here in our acceleration term? We have an s. So that means we're using v dv is equal to ads. But what else are we noticing? We're noticing that if we wanted to rewrite this entire thing, right, we can get rid of this s, make this just k delta. We haven't changed anything, by the way. Minus ks over this term is equal to a. And what do we know about this term? Well, this is a constant term. So I'm going to represent this term with a constant h. And let's just drag this here. this is a constant h. As you can see, when we're dividing out everything, we're going to get a very clean bit of numbering here. So we don't know what k is, so k is going to stay as a variable, but we're going to get that h is equal to 0.1k because delta is 0.1. Yeah, delta is 0.1 k, 0.1k. What the hell? I don't know why I started so much. Also, we know that mb 0.2 plus mp 0.8 is 1. So we can actually just ignore this term. It's just 1. Plus, and now we just calculate the rest of this stuff very easily. We have a g for each of these, so we can drag out the gravity. And yeah, we can combine the sine terms because they're both sine terms. We get mp negative and we're taking out a negative, so minus 9.81 to make it all positive. This is 0.2 sine theta plus 0.8 sine theta, so just plus sine theta, and this is mu k. So we're going to go square bracket here. This is going to be 0.1, which is the coefficient of friction, mb, which is 0.2, cosine of the angle is 40, plus sine 40. And this happens because mb and mp added together are 1. This is all over mp plus mb, but that's just 1. That gives us an h, which is equal to, if I just plug this into my calculator here quickly, negative 9.81, bracket, 0.02, cosine 40, plus sine 40, double bracket, negative 6.46. Negative 6.46. So 0.1k in front, because I forgot to rewrite that. 0.1k minus 6.46 is equal to our h term. So we're going to now take this. V dv is equal to a is now h minus ks. And mp plus mb is just 1. So we're going to ignore that. So we're going to go minus ks. So h minus ks ds. And this is h, so I'm just going to substitute this in and bracket it out like this, minus ks ds. And now we integrate both sides like this. They start at 0 because it's at rest initially, as stated in the problem here. At rest at the initial position s equals 0. So our initial conditions are 0 for both. That looks like a sigma. We go up to a variable velocity because it says that our final velocity is equal to this term. So we're trying to prove that it is actually, in fact, equal to this term. And then s equals delta. So you can plug in delta here, which is also 0.1, right? That is an easy integration. You're going to add an s term to this, and you're going to make this s squared over 2. Nice and easy. If you want to just like make things easier on yourself, multiply everything by 2 right now so that there's no 2 here. So we do our integration. We're going to get v squared, and I'm going to put my delta here because this is v as a function of s, where s is delta, is equal to, so we're going to get 0.1k minus 6.46 s, and because I wanted to not have a fraction, we're going to put a 2 there as well, minus k 0.1 squared, right? And if we do this, s here is delta. This was supposed to be an s squared. I plugged in this is supposed to be delta, so another 0.1, right? So we do this calculation, we're going to get 0.2 times 0.1, so 0.01 minus 0.1 squared is 0.01. So 0.02k minus 0.01k is equal to 0.01k, and 6.46 times 2 is, let me see, times 2 times 0.2 is negative 1.29. So minus 1.29, right? And if we look at what the question has told us, AK minus B. A is 0.01. That matches. B is 1.29. That also matches. Which means we got the question correct. We've proven that we are smart. Let's go. Okay, F. During the second phase, when the block is no longer in contact with the spring launcher, write an expression for the acceleration of the block in the I direction. So we can ignore the J's for this question. Nice and easy, ignore the J's. So we can actually go back to our block I acceleration right here. What has changed about this acceleration? Well, now there's no more contact, right? And yeah, that's kind of it. That's all that changed. We can cancel out mass of the block because that's in every term. Also, I need to bring the NB, which was this minus the mass. So just this, and cancel out this MB. Okay, we can plug out a G if we wanted. So to simplify this, it's negative G of mu, and I'm going to get rid of the K, mu cos theta plus sine theta. And there you go. That is an acceleration expression. So we're just taking the last formula and getting rid of the contact force. Nice and easy. G, determine the velocity of the block immediately before it is launched off the incline as a function of k. Express your answer in the form v of L squared is equal to ck minus d, where c and d are constants with these units. So we don't know what the values of c and d are. We're solving for them. Yeah, the units should make sense if we get the right answer. So again, we have VdV equals ADS. Well, if you look at that, we have ourselves A right here. So let's integrate. We get, also, it was not over here. I made a little speaking error here. This is not randomly multiplied by 2. When you integrate v, it becomes v squared over 2. So you're just dragging the 2 over to this side, which cancels out the fraction that was on ks squared over 2. That's all. So, anyways, let's just quickly do g. So again, we're going to be integrating a, where a is this. As you can see, there's no s on here, so it's just going to be this s. And we're going to take the 2 over to the other side as well, again. So we're going to have, and we're doing this from delta to L. So S is from delta to L, and V is from V delta to VL, right? So we have V delta as well, which is this term here. This is V delta. So V of L squared minus V of delta squared, and remember this is over 2, but I'm going to be dragging the 2 over to this side, is equal to, I'll just get this, 2, and this is L minus delta for the S term that appeared. So now we just need to plug in our values and solve for V of L squared. So we're adding V of delta squared to both sides. So this is equal to this. And we're going to have negative 2 times 9.81. Negative 2 times 9.81. Sorry. Mu is 0.1 cosine 40 plus sine 40. And then L is 0.4 minus delta 0.1. And then plus this. So 0.1k. Yeah, plus this. Like so. Which, when we simplify, we're going to get V of L squared is equal to, so 0.1k stays the same, so 0.1k. And now we're going to have 2 times 9.81, 0.1 cos, this thing, so this is 0.3 times negative 2 is negative 0.6, and then I don't know why I'm speaking as if I can do 0.1 cos 40 inside. Let me just get the calculator here for this. So negative 2 times 9.81 times 0.3, 0.1 cos 40 plus sine 40 brackets minus 1.29, which gives us negative 5.52, so minus 5.52. And that's a constant term. And if we check, it is in the form ck minus d. You can check the units. It has to be in meters per second squared, like meters per second squared. Well, this would be because it's an alone term. Anyways, final thing is h, where your co-designer handled the projectile calculations and determined your launch velocity needs to be VL squared equals 2.14 meters per second squared. What value of spring constant K do you need to launch in the cup when theta equals 40 degrees? So we get that V of L squared is equal to, as stated, 2.14 meters per second squared, right? What else do we have that V of L is equal to? V of L squared. We have it's equal to this. So it's equal to this. So then we just go 2.14 plus 5.52 divided by 0.01. We get that our spring constant K is equal to 766, and the units for spring constant are newtons per meter. And that's the first question. Very long question, but I think it is a good question that goes over everything that needs to be gone over for like these kind of problems, right? Because we had the free body diagrams, we had acceleration, we had forces, we had friction, spring constant, delved into all the forces. So good stuff, right? Anyways, let us get to, and now we just delete everything here. Okay, on to the next question. So the 50 kilogram crate shown in this figure rests on a horizontal surface for which the coefficient of kinetic friction is 0.3. The crate is subjected to a 400 Newton towing force as shown. Determine the velocity of the crate in 3 seconds starting from rest. Okay, so step 1, and this is Q2. Step 1 is draw your free body diagram and your kinetic diagram as well. So, so I'm going to say FB means free body and K means kinetic. So we're going to have a square, because even though you might think this could be in 3D, this is a flat. This is flat. So you can do it in 2D. So we have our P at an angle of 30 degrees, which means we also have a normal force N, and we have the weight mg, and we have a little friction, which is F of K. Now we have also, I'll switch colors here. We have a P in the X direction and a P in the Y direction. So we need to keep those in mind. Now let's think about our kinetic diagram. I'm going to change our box to a point for the sake of this one. So, is the crate moving up and down? No. How do we know that? Well, because it's not said to be moving up and down. And if you just think about it, if you're towing a box like this, wrapped around the center, and the forces are getting distributed like this and whatever, it's going to be going this way. It is moving because it's kinetic friction. And this is MA in the X direction. So now we can actually get to calculating. So in the X direction, so we have Fx is equal to M of AX. I'm just going to call it A. So it's equal to MA, which is then equal to, let's look at our forces in the X direction. We have PX and FK. So px, and we're taking this direction to be our positive. I should define it as such. This is our positive. Minus fk, right? And now we can change px into p, and if we look at it, cosine 30, p cosine 30 minus mu, and I'm not going to add the k because there's no mu s to get confused with, mu n. So we need to also calculate n, and to do that we need to use the fy force analysis. So fy is equal to 0, which is equal to, so we have py plus n minus mg. And we can change this into p sine 30 plus n minus mg. So we are solving for n. So n is equal to mg minus p sine 30, which is equal to, so mass is 50. Gravity is 9.81. Minus 400, sine 30 is a half, so minus 200. So let's just get this into a calculator. 50, 9.81 minus 200 gives us 291 newtons as our normal force. So we take our 291 and we sub it into here. Divide everything by mass, by the way. So we're going to get that A is equal to, after dividing out by mass, which is 50, we're going to have px, which is p cos 30. So 400 over 50 is 8 cosine 30 minus 0.3 291 over 50. Okay, I don't know what that is off the top of my head. So 0.3 291 over 50, which is equal to, let me see. So 8 cosine 30 minus 0.3 times this over 50, which gives us an acceleration of 5.19 meters per second squared. 5.19 meters per second squared. Determine the velocity of the crate in 3 seconds starting from rest. So we can assume that this is a constant acceleration, which means you go back to our kinematics equations, right? And we want final velocity. Well, it starts from rest, so that means v naught is 0. And we want vf. So v is equal to at after 3 seconds. So it's equal to 5.19 times 3, which is it's going to be like 15.6, which is equal to 15.6 meters per second. And that is question 2. That's all there is to it. So let's just bar this off. Q3. Right, so question 2. Good question. Remember free body diagrams, and okay, you don't always need a kinetic diagram. Like intuitively, I mean. If it's a written question, you should always include your free body kinetic diagram. But like intuitively, I feel like you don't really need a diagram to show that force that is moving this way, which means the acceleration is this way. I don't think you really need that intuitively. If it helps you, by all means, use it. If something helps, you should use it. Like there's no reason not to use something that's helping you. Anyways, next question. Oh, this one's kind of blurry. That sucks. Okay. A skier from rest on the 40-degree slope at time t equals 0. What? Oh, okay. English. Starts, not start. End is clocked at t equals 2.58 seconds as he passes a speed checkpoint 20 meters down the slope. Determine the coefficient of kinetic friction between the snow and the skis. Neglect wind resistance. So, let's do some fun stuff. Let's set up an x and y plane. Well, he's going down this way, right? And he's not moving up at all. So the y is, you can ignore the y entirely if you want. right? Let's just call this x. Oh, wow, that is not a straight line at all. As I was saying, let's just call this x. And I'm sure someone's happy I actually use a straight line tool instead of drawing out a really clunky line. 40 degrees. This is our x-axis, which means, of course, gravity is going to be affected by this. So, yeah. What do we want? We have a t naught. We have a t final. We have an s. We don't know acceleration, right? But we can get acceleration with forces. We don't know our mass, by the way. We do not know the mass of the skier, but we don't need it. This is where it gets fun. You don't need mass. Okay? So let's draw our free body diagram. Free body. Now, our gentleman skier here is going to be turned into a dot, because that's the only value he has in physics, is a dot. We know that there's friction, and it's kinetic friction. We know that there's gravity straight down, mg. Now you're probably saying, oh, there's gravity, but it's okay, we don't need it. Right? And we have a normal force, like so. Those are the forces on our skier. Now you might be thinking, isn't there the force of him moving this way? No, that's accounted for in the kinetic diagram. Because remember, F equals ma. Well, let's look at our kinetic diagram. Wow. ma. Wonderful. Anyways, let's do our force analysis. In the x directions, right? And I'm going to skip out writing this every time. Okay? Because it is not necessary to write out every time. But, also this angle is 40 degrees. Yeah. So, yeah. Okay, so we're going to get that. Also, keeping in mind our scale here, right? Like our axes. If this is 40 degrees here, and this is 90 degrees, this here becomes 50 degrees, right? Or you can have your 40 degrees here. For this question, I'm going to show this method, because both methods are valid for the angles. If you have sine 40 and cos 50, those are the same thing. And I'm going to double check that with my calculator just to make sure I'm not being an idiot. Cos 50 and sine 40. Yeah, like I said, those are the same thing. So you could do whatever way you like. If you would prefer to have respect for the given angle, you would use this 50 for all of your things, for your weight components. But I'm going to use the other one just to demonstrate that that's not what's happening here. So, in the x direction, our forces are, we have an acceleration, which we've said, ma is equal to, now we have fk, so that's just going to be mu n. This is negative, by the way. So we have mg cosine 50 minus mu n. Now, here's an issue. We don't have mass, right? How are we supposed to solve this? Well, let's look at our y force balance, right? This is balanced because he's only moving in x, right? Because remember, our y is this. Is he moving in y? No, he's moving along the x-axis. So our y totals out to 0, which means our normal force is equal to mg sine 50. Also, yeah, mg sine 50. Or if you wanted to, you would go cosine 40. It doesn't matter because those are equivalent. They're the same thing. Sine 50. Just for the sake of keeping the same angle, I'm going to use sine 50. So now let's rewrite our equation. ma is equal to mg cosine 50 minus mu mg sine 50. What do we notice? All the masses cancel, right? All the masses cancel. Excellent. That is beautiful. Now what are we missing, right? We have gravity. That's 9.81. Cosine 50, sine 50, those are constants. We don't have acceleration. We don't have the coefficient of friction. What are we solving for? The coefficient of kinetic friction. So we need to solve for acceleration. How? Using this information. Time, time, distance, and initial velocity. This is 20 meters. He starts from rest, so V naught is 0, S is 20, T is 2.58, minus 0, 2.58, and we're solving for A. So what formula does that make you think of? Well, it makes you think of S equals S naught plus V naught T plus half AT squared. So we have S is equal to 20. Those two things are 0. And we have a half A T is 2.58 squared. So we're going to go 40 divided by 2.58 squared. 40 over 2.58 squared, which is 6.01 meters per second squared for acceleration. So 6.01 meters per second squared is equal to A. And we're solving for this, so we're just going to plug this into our equation. But let's rearrange quickly. We're going to get that mu is equal to so this is cotan 50, because we go flip these around, right? And then divide by g sine 50 on both sides. G's cancel. Cos over sine is cotan. So cotan 50 minus A over g sine 50. So that gives us a mu is equal to whatever cotan of 50 is. I need to calculate that quickly. So cos 50 divided by sine 50 minus this divided by 9.81 sine 50, which gives us a coefficient of friction of 0.0394. And that is to 3 significant figures. That was a good question. These questions, the theme they follow is you're going to have one part kinetics, one part kinematics. Like you can tell we keep dipping into kinematics for each of these questions to solve for something. In this case, it was acceleration. Well, I mean, that's the only thing that's useful from these is the acceleration. So saying anything else was kind of pointless. But yeah, as you can tell, kinematics still play an important part even when we are analyzing forces. So on to Q4, which is this one. So, oh, that's too much zooming. Okay, a car is descending the hill of slope theta 1 with the brakes slightly applied, so this V is constant. Slope decreases to theta 2 at A. Driver does not change the braking force. Determine the acceleration after it passes point A, and then the angles are 6 degrees and 2 degrees. Whoa! So, we are going to have to draw more free body diagrams. But let's split this into 2 sections right across point A. This line is A. Part 1 and part 2. So we're going to have a free body diagram. And this is for part 1. And the kinetic diagrams. And one stays in line. So we are going to... And again, this is 6 degrees. Theta acts like this, and theta acts like this. 6 degrees, 2 degrees, right? So let's get our car. And our axes are going to be in the direction of the car, like this. So like this, like this. And this is dotted to represent axes, like this. And like this is... Wow, that was awful. So I'm going to say F for braking force. I'm going to go straight down and say mg. And again, the thing with the triangle, right? We have a triangle like this, 6 degrees here, 84 degrees here, or 6 degrees here if you'd prefer. I'm going to go 84 here because I like to have my x's be in cosine and my y's be in sine. Does it matter? No, it's just preference. So this is 84 degrees here. So we have mg and we have n, of course, along the y-axis. This is x and this is y. And now, which way are we moving? Huh? Determine the acceleration of the car after it passes point A. So we have our car. And the kinetic diagram, we have no acceleration. Because v is constant. So we have no acceleration. This is what our kinetic diagram looks like. If you want, you draw your axes, but I don't want to. Now for part 2. Okay. Same thing. We're going to continue to have F, the braking force. We're going to continue to have N, the normal force, and we're going to continue to have mg. And these are here to signify axes. The angle changes to 88, and that's all. Now for our kinetic diagram, we need to determine acceleration. So what does that mean in terms of acceleration? Well, we could have an acceleration this way, or we can have an acceleration this way. Determine the acceleration A. Yeah. So these are the two directions we could have an acceleration. If it's negative, then that means this is correct. And if it's positive, that means this is correct. So let us calculate. And keep in mind, we don't have the mass of the car. But as shown in question 3, you don't need the mass. So let us do this. So in the first part, so using the free body diagrams from this part, we see that there are no accelerations, which means that the forces are all even and equal to 0. So that means that F is equal to mg cosine 84, and N is equal to mg sine 84. Nice and easy. I don't know, we don't need the normal force though, but I just wrote that out. So this is for part 1. Now for part 2, if we do our analysis, we know that it's equal to MA. So MA is equal to, why am I getting notifications? Anyways, MA is equal to mg cosine 88. If we look at our diagram here, the weight is this way, which we've defined as the positive, and F is this way, which we've defined as not the positive. MA minus F. And we know that F is mg cosine 84, so let's just plug that in. And as you can see, again, all the masses cancel out. And g is just gravity, 9.81. So we plug this into our calculator. So 9.81 cosine 88 minus cosine 84, which gives us a acceleration of negative 0.683. Yeah, that is, are these in cosine? Cosine and cosine. Yeah, that's correct. Okay, no issues here then at all. That's the question. That is our thing. I guess technically, we're not explicitly given gravity. We don't even know if we're on Earth. So if you want it to be more exact, this is the same thing as writing. Okay, that doesn't even matter. I don't know why you wouldn't assume gravity is 9.81. So moving on to the next question, Q5. So Q5, let's just get rid of all this. Q5 is this one. A small package is deposited by the conveyor belt onto the 30-degree ramp at A with velocity of 0.8 meters per second. Calculate S is down here, on the level surface BC at which the package comes to rest. Coefficient of kinetic friction for the package and supporting surface from A to C is 0.3. Okay. That is all there is to it. Again, we're going to split this into two parts. Right here. That's right here. This is part 2, and this is part 1. So, let us start with the free body diagrams and the kinetic diagrams. So for 1, we have a free body and a kinetic. So we have our box, and is sliding down here, right? A distance of 2 meters. It has a friction, Fk. It has an mg. Wow, that's not an m. It has an mg. It has a normal force. And then kinetic diagram is ma in this direction. And just for simplicity's sake, I'm going to define this to be my positive here, like this. And then for part 2, we have the block is now on a straight thing. We have N, we have mg, and we have a friction force, Fk. So if we look at our kinetic, which way is it going to move? Well, it will be going this way for ma. Okay. Time to calculate. So, sorry, I blanked for a second there. Time to calculate. Let's go back up. We have velocity and we have a distance. This is hinting towards kinematics, by the way. Velocity and distance. Where's the distance here? Velocity and distance. We know S naught is 0. S final is 2. VF is 0.8. It's constant. But yeah, we'll get to that when we need it. Let us do our force analysis. So for part 1, the first section, we have in the x directions that it's equal to ma, positive ma, is equal to mg, and again we have our angle here. It's like this. It would be a angle of 30, or yeah, the angle of 30 is here. Sorry, this would be an angle of 60. I'm not going to write that. Here, an angle of 60 degrees, because 30 is here, right? And we're extending, so 30 is here, straight line up here. This is 90, 30, 60 here. So we're going to get that ma is equal to mg cosine. Oh, that's what? What's this? Where did the circle come from? Anyways, mg is equal to cosine of 60 minus, we have our friction, and we just know that's mu n, so I'm going to write that as mu n. We don't know n yet, so let's look at our y directions. We get that there's no acceleration in y, so it's just equal. So n and mg sine are equal. So n is equal to mg sine 60. So we can sub that into our equation up here. Mg sine 60. All the masses cancel. Very fun, very fun. And we get this nice acceleration equation, which we can calculate because we know gravity and we know the coefficient of kinetic friction. So calculating this out, we'll get cos 60 is just a half, so 4.985, which is half of 9.81, minus 0.1 sine 60. Wait, no, it's 0.3. Minus 0.3 times 9.81. 9.81 sine 60, which gives us an acceleration here of 2.44. Wait, 9.81 over 2. 4.905, not 985. Oops. So that gives us a acceleration of 2.36. 2.36 meters per second squared. Okay. Now we look at part 2, where we're going to have in x, we got to scroll down. In x, we have a acceleration. In y, we have no acceleration. So we'll keep that in mind. So in x, we have that ma. And for this, I'm going to keep up the fact that x is, like if we were to imagine that the thing sloped, our positive x would continue being to the left. So let's redefine here as positive. Either way, the negatives are going to cancel out. ma is equal to mu n. And in the y, we get that n equals mg, which is equal to, do we have the mass of the block? No, we don't. Uh-oh. That's okay, though, because when we plug in mg to here, the m's cancel. We don't need the masses. So yeah, see, this is what I said earlier. You see that there's no mass, and you might panic a little. Like I did. But it's okay. So here A is just equal to 0.3 times 9.81, which is just equal to 0.3 times 9.81, which is 2.943 or 2.94 meters per second squared. And this should be, I'll call this A2 and I'll call this A1 just to avoid confusion. So we need to find the distance s. So to do that, we need to find the time, the velocity, not the time, the velocity it takes to get to the velocity at the end when it gets to B. So you can use that as our initial velocity here to find the distance it goes here. So we know that Vf squared, and I'm going to call it V squared, is equal to V naught squared. So V naught squared plus 2a, s naught is 0, so just 2as. So V is equal to the square root of 0.8 squared plus s was 2, so it's going to be 4 times 2.36, which is equal to, so square root of 0.8 squared plus 4 times 2.36, which gives us a velocity of 3.17 meters per second. 3.17 meters per second. And then we use the exact same equation. So I'm just going to skip ahead, and I'm going to call this Vf because it is actually the final velocity. Vf squared is equal to V squared plus 2a s minus s naught. S naught here is, we can consider it to be 0. Because it just wants to know how far from B does it travel. So B is our new 0. So we'll get rid of s naught and just make it s. So rearranging for s, we get Vf squared minus V squared over 2a. And let me just brackets here. Over 2a equals s, which if we plug in our values, because we know it comes to rest, so Vf squared is 0. So it's actually just like negative V squared over 2a. I forgot it came to rest, but good thing I looked back at the problem statement. It comes to rest, so we get this. Since it's distance, we can ignore the negative. And by ignore the negative, I mean, well, we shouldn't, but the acceleration is negative, right? Because think back to the, the kinetic diagram. We've defined the acceleration as negative, so I'm going to get rid of the negative here. So we have V squared, which we got, so 3.17 squared over 2 times, what is it? 2.94, which gives us 1.71 meters as our final answer. 1.71 meters as the final answer. So, from B, it traveled 1.71 meters to arrive at C. Very nice. C is 1.71 meters. Now, if you wanted to calculate how far it went from A, well, you would just like take your 2 up here. 2 plus 1.71 is 3.71. So it went 3.71 meters from the origin. Okay, final question. The 10 kilogram steel sphere is suspended from the 15 kilogram frame, which slides down the 20-degree incline. If the coefficient of kinetic friction is 0.15, compute the tension in A and B. Now, this is certainly a question. That is interesting. Okay, let's see what we need to do to figure this out. So, we have two tensions here acting on the ball. Tension A and tension B. So that means the tensions are acting like this towards it. And let's make those arrows. So I'm going to call it A and B for our forces, so I don't need a new label because there's already an A and B there. So very nice. Very, very, very nice. So there's a ball and there's a frame. I'm going to call this frame F, and the ball is just going to be, I guess it's a sphere, so I'm going to call it capital S. So, time to calculate, and before we calculate actually, we're going to do free body diagrams and kinetic diagrams. Kinetic diagrams. So let's start with the frame. In terms of its free body diagram, it is like this. From itself, it has 1 TB, if you look at it. If we consider the particle to be like this, that means TB is acting at this angle and TA is at this angle. So this is B and this is A, and they're both at 45 degrees from the origin. So I'm just going to call this 90 degrees and put a line here. We also have an mg on the frame which acts at 20 degrees like so. We have a normal force acting straight up like so, and we have a force of friction which I'm going to call lowercase f like so. Overall, how's it moving? This way, MA. Now, this is a really messy free body diagram, right? So when you're actually drawing it yourself, make sure you are much more clear than I am. Oh, that's a big eraser. Don't make this a 90-degree angle. That was a laziness. Label it both as 45s, right? Because even here you can see I missed the center when I was drawing this line. So this is technically not a 45-degree angle. But that is okay, because now we're going to look at the sphere. And for the sphere, we have it like this. We have a TA pulling on it like this, and a B pulling on it like this. And again, there's a 90-degree angle between them. There. And we have an MG straight down. And those are the only things acting on the sphere. And the sphere, it follows the ball's movement, so it's accelerating down this way. I mean, it follows the frame's movement, so it's accelerating down this way. Anyways, let's get to some force analysis for the frame in the x direction. And x is along this line. This is y, and this is x. So let me just, here we go, x and y, down is positive, up is positive. So, in the x direction, we have MA is equal to, right, we have mg sine 20 plus a cosine 45 minus b cosine 45. If you think about it, to get into the x direction, these both have, I mean, either way, sine 45 and cos 45 are exactly equal. So that doesn't really matter, actually. Use whatever you want. Those things are equal. Minus mu n. Now, in the y direction, what do we have? Well, we have that there is no y acceleration. So n is equal to mg cosine 20. So hooray for that, right? Hooray for that. Make sure, by the way, this is also incorrect. Oops. The total sum is 0. That is correct. But I actually forgot that tension exists. So, hooray. And what are we solving for? The tension in each of the wires. So we want A and B. Right? So we have 0 is equal to, and n is in the positive direction, n minus mg cosine 20. And then we have minus, and I'm just going to take this to be cosine 45 a plus b. I don't know why this isn't capitalized. A plus b. Because they're at the same angle. We can do the same thing up here, by the way. So I'm just going to do that here. Cosine 45. This becomes a plus like that. I mean a minus, sorry. Because, yeah. It was minus b cosine. Yeah. So a minus b and a plus b. Well, we have two equations now, but let's just wait for now. Okay, let us wait for now. Let's look at the sphere, not the ball. I keep saying ball, but b, I don't want to reuse b. So in the x direction for the sphere, we have an acceleration ma, which is equal to cosine 45. And if we look at it, b is in this direction, a is in this direction. So it's going to be b minus a. Because remember, the positive x is this way. A is acting away from the positive x. So it's b minus a plus mg sine 20. And then in the y direction, it's also 0, is cosine 45. So in the y, they both act towards positive y. So a plus b, there's an equal sign missing, equals, and then minus mg cosine 20, right? Because if we think about it, 20 degrees is here, cosine mg cosine here. So what do we notice about all of these equations, right? We have a plus b, we have b minus a, we have a plus b, we have a minus b. So there is a lot of rearranging. There's a lot of rearranging to do. You would rearrange these for AB, like the n for AB, or what you could do is add these terms because they'd cancel, and you get n is equal to, actually I don't remember if, is that allowed? I don't think so. You want to look at equation 4, this one. This is the fourth equation, right? Rearrange for a plus b. So that's going to be mg cos 20 over cos 45, right? That gives you a plus b. And we get that a plus b is equal to, let me put that in my calculator, 130.4 newtons. Okay, that's a plus b. Now, we have a plus b. Where do we have a plus b again? We have it in this equation. We can solve for n, right? So we just add these things together. So we get mg cos 20 plus cos 45 times 130.4, which gives us an n that is equal to 230.5 newtons. Right? Yeah, okay. I read that correctly. Good. And finally, we need to look at our we have n. We can plug n into this equation, which gives us a minus b with rearrangement. And then once we get a minus b, we know that b minus a is just negative a minus b, right? But we get that a minus b is equal to 19.6 newtons using this equation here, because we know everything. And then we have two unknowns, two equations, so it's solvable. We can do elimination. So add this equation and this equation. We get that a is equal to, or wait, sorry. The accelerations are equal. You would solve for the accelerations in these to solve for what a and b are. In these accelerations are the same. A minus b and b minus a, right? So if you have cos 45 a minus b, you solve for the accelerations because they're equal. And then that would get you what a minus b is. Because this is just negative a minus b. So you'd make this negative. So you get cos 45 a minus b minus cos 45 a minus b. Something like that. But it allows you to solve for what a minus b is equal to, which we got here, 19.6. And then you would have to rearrange the equations again to get a is equal to, so when you add them together, you get 2a is equal to 130.4 plus 19.6. So divide that by 2, gives you 75.0 newtons. That's rounded, by the way, to 3 significant figures. And then you would just do 130.4 minus 75 to give you 55.4 newtons for B. B is equal to 55.4 newtons. And that is that question. Is there another question here? No, there is not. Okay. So those are all the questions, all 6 questions for this chapter. As you can see, it is getting a little, I'm losing track of things while I'm doing my work. Maybe if I was actually writing stuff down, it would be a bit better instead of typing. But I don't have a tablet, and I'm not going to buy one. So this is what we make do with. And I kind of like typing up questions. It's like a little, it's like it's unique, I guess. I don't know who else is doing this, right? Except for me, guys. Okay, I'm gonna stop talking now. Bye. Thanks for watching. Hope you learned something. Thank you. Bye.